Hello everybody and welcome to this video. This video is our demo for the assignment 2 of the data visualization course. My name is Vijay Jasankar and my mobile number is IMT20195525. So in this video, the agenda is we'll look at the README and then we'll look at all of the files and then we'll see a few of the videos which we have generated. And at the end, there's also a special twist which involves sound. So we'll see how that pans out as well. So let's get started. This is the folder structure. So we have the documents which contains the assignment document. We have experiments, which mostly has a lot of these pre-processing and also post-processing steps that we use to enhance the visualizations. And then we have the outputs folder, which as the name implies, contains the outputs of all of the images. We also have pickle files, and pickle is used to store certain objects which are used, I would say, transcendentally across different folders. We also have presets, which carries over from our first assignment where we had the .ini configuration files from which we load parameters into the visualizations. We also have scripts, which contain all the visualization files, and the sounds, which like I mentioned before, has a few of the audio clips, and videos which contain the animations. So the README files has a lot of these instructions about running the files, generating the videos, the sounds, and so on. It also has a few sample visualizations, which we will see in the videos also. So let's get started with the experiments. The first thing we did was actually choose what files to plot from. So there were a lot of files, and the thing is this assignment had really large files themselves. So plotting them was quite a challenge. So choosing the correct subsample was quite important, which is where file choice comes in. Much like last assignment, we basically took the index of each file. So for example, if you look at this file, so the index of this file would be 1 and so on. So we went and looked for papers or other articles regarding the tsunami, and we found this one, the NOAA Center for Tsunami Research. And this PDF document basically tells us the exact date of the tsunami. And from there, we could estimate the index of that file, which was 73. And so we have three rules now. We take the absolute difference of the index of a particular file with 73. And if that index is less than or equal to 30, we take that file. If it's between 31 and 60, we take every other file, so alternate files. And if it's greater than 61, we take 1 in 3 files. And for the scalar fields visualization, this was actually subdivided into half again because of computational constraints. So this generated around 100 files, which were used to generate all the plots. Up next, we have depth choice. So in a lot of these examples, as you would see, we kept the depth constant and we sampled over time. So each file is a different time step. So to choose the depth, we had a depth range for these isosurface values and a constant depth for the streamlines. So to find the depth range, we basically plotted how many possible attributes you can get or how many possible things are in the data loader. And when we plotted that, we found out that it looked like this. So we can see 50 was the optimal thing in terms of it has a decent amount of parameters to plot and it would not be too computationally overbearing. So we took the max depth as 50. Now, after that, we also have image helpers, which will come into play later. So basically, if you want to combine two images, so if you have slice A and slice B at a different depth, if you want to combine them, you can combine them by giving them weight. And this is from OpenCV. Next, we also have sound player, which basically plays sound if you give frequency or if you give some kind of array. So the one caveat with this is if you give constant values. So for example, 1, 1, 1, 2, 2, 2, 3, 3, 3, the sound is actually quite indistinguishable because it's very low. So what we typically do is add some kind of noise, like you can see over here. You add for each value in the array, you basically add a random value which has a range of minus 1 by 10 of that to plus 1 by 10 of that. And this generates some very interesting audio examples as you would see in the future. Now, the exact fraction of this would determine how much of a random sample you are adding. So we use 1 by 100 and 1 by 10 in our audio files to generate two different ones. Next, we also have tsunami sound. Like I said, this basically takes an array at the end. So this loads everything and it takes the zonal value of the current, meridional value of the current, computes the magnitude and plots the magnitude as a sound array. And this will come into play very soon, as we shall see. Next, much like our previous assignment, we have abstracted away the loading part into a separate file. So data loader. So as you can see, the basic archetype of our data loader has the expected extension of the file, and it also has warning flags. So right now we use bad flag to determine whether something is not supposed to be plotted or it should be replaced with NaN values, and it can be extendable. So this is a dictionary here. So we have one for salinity, one for temperature loader, one for zonal currents and meridional currents. And this is actually very similar to our previous assignments data loader. Nothing very special here, except for a few twists. And the few twists comes in form of this depth value. So for meridional and zonal, so for our current visualizations, we expect both files to have the same index and date, and also at the same depth value, because we're taking the same depth over all the times. So we basically filter over depth value here. And like I said about the graph earlier, in the previous loaders as well, we have min depth and max depth. So you can see max depth is stuck at 50, min depth is minus 50, and basically it samples across that range now. Next, we also have feature extractors. So we've actually reduced the number of files, increase the number of files here. So we have a base feature extractor, which is here. So you can see the archetype again requires an input dict, and then we also have a method like get data, or it's called get values also in some other files, and generate and save plot. So the comments are pretty self-explanatory over here. And these are the two main functions basically. So what this does is, if you want to plot something, you return an ordered dictionary of all the arrays or all the values you should possibly need, and you basically load them up here and create the plots. Now let's look at the presets. So much like the previous assignment again, we load certain attributes of the graph from a configuration file. And in that case, this is experiment1.ini. So sal iso stands for salt iso service and so on. So all of this has been documented in the README file as to how you can possibly change or customize your plots. So this can be checked out if required. Now let's look at the files themselves, and we'll have a closer look about how these plots are generated. So I'll look at isosurface feature extraction first. Let's look at the salinity one. So basically, this returns the longitude, latitude, depth, and salt values, and also the ISO min and ISO max have been taken from the minimum and maximum of this scalar field. We also have count, we have a color scale, we have flat shading. So this is how the things are rendered, and we also have the opacity. And a lot of things have been derived. So for example, this on surface count, you can take it straight from the config file. And this is also about potential temperature. Now let's go on to our current feature extractor. So this is for the vector field. So as you can see over here, the treatment is a little bit different, but it's very similar to our quiver plot we made for the last assignment, where we had a matrix for both meridional and zonal, and we populate that matrix based on whether the value exists in the latitude and longitude, and then we create a mesh grid from that. These two lines were added because of the y-ticks issue. Apparently, the number of entries in both these arrays should be the same. So we created a linspace for that with the length of these two. Then we created a mesh grid like we did before, and we also created a base map, which is basically like a geographical map, which has coastlines, which has the latitude and longitude axes. And again, we can configure the line width of that. And then we created a stream plot, and we saved the plot. So lat log equal to true was a true game changer for me. I did not know about this feature until I looked at the documentation, and I found it very nice. It basically aligns it to the latitudes and longitudes, and it produces very nice plots. So that was about the files itself. Well, I forgot about this one, video generation.py. Much like the last one, when you load up all the files from the pickle file which we saved earlier, we load up the files, and then we start to call the loader, create the features, and call generate and save plot. So this is the standard procedure we do for 3 of them. And then same for vector field, and video generation basically makes the video. So this is from FFmpeg, and we used 1 FPS for some videos and 2 for the others. Next, we also have a report which has a lot of the visualizations. And more than that, it also has more details about the subsampling method which I just spoke about. And it also has a lot of the observations, so the before and after pics, and it also has the answers to some of the questions. We also have two external references, one which I have already alluded to, the NOAA website, and the other one is this paper by Papaleo, I think it's pronounced that way. So basically, I use this just to see how certain plots look like, and I'm not sure this will render. Yeah, I just use this paper to see how certain plots looks like and how they use color maps, and this really was the source of inspiration for a lot of the color maps which you would see in these plots. Now, like I alluded to earlier, we do have videos for each thing, and so let's look at a few of these videos. So the potential temperature video is loading up. So we can see that this is visualized at a constant depth, and you can see that these color maps basically keep changing over time. And this is at a depth of 5, so you can see the change, and they become basically bigger as time progresses. So the temperature becomes higher, which is also noted in the observations. And next we have salt. And one good thing about this salinity values is it was exactly in conjunction with what we have for the SSS feature of our first assignment. So that is pretty interesting. So as you can see, this also progresses. And then we have the isosurface video. I'll show you this salinity video for this demo. So you can see, so if it's empty, basically it's an NaN value at that point. So you can see it progresses that way. And similarly for your temperature. Now we come to what I found the most interesting part of this assignment, that is streamline. So we have two different types of sampling. The first one is at constant time. So we sampled one particular video at different depths, as you can see, 25 meters, 35 meters, and so on. And actually, there wasn't that much change in the direction, but the magnitude and the relative density of these fields did change, which was pretty interesting. And again, it has been noted in the observations as well. And next, we have constant depth. So constant depth, like I said, we kept a depth value and we changed the files according to the pickled files, all of those 98, 99 files. The reason I said 98 files is that one file actually did not exist in meridional where it exists in zonal. So we took care of that also. So we can see that the direction has changed to some extent as well. This could be because of monsoon and also the tsunami. But we've seen all of these files and we see a lot of the change in the direction and we see a lot of the change in depths. But I was fundamentally lacking a very nice explainer for the tsunami itself. Was there a direct impact of the tsunami on the streamlines or on the currents or maybe the magnitude of those currents? And that gave me an idea. Why not take the magnitude of the current at the epicenter of the tsunami point and then make that into a sound file? So what that means is basically, if we have 5 dates, let's say we have 3 days A, B, C in order, we'll find the magnitude for A and make it like this. So this whole array will be filled with the magnitude of A, and then for B, and then for C, and so on. So this will be full of 0.5s, this will be full of 0.1s, for example, and 0.4s. And we can take the sampling rate of the particular sound, in this case 44,100 hertz, and we'll create a very lengthy array which consists of 0.5 repeated so many times, 0.1 repeated so many times, and 0.4 repeated so many times. And the hope is that when we look at the epicenter of the tsunami, it has somewhat of a Doppler effect. So we have something like this, and then we have a swoosh, and then it goes down. And I'm very thrilled to say that we did observe something very similar. Now, granted, the caveat from before still exists, that if the array is filled with only these 0.5s and 0.1s, we would not hear much, which is why we need to have a little bit of a disturbance. So we have a little bit of a random disturbance between this. But overall, around the 76 mark, we did see the little bit of a bump, a little bit of a swoosh, or a little bit of a change, what I call Doppler effect. So let's look at that video as well. I'm not sure if the audio will catch that. So there was a distinct hissing / static sound in the background, and that corresponds to the magnitude of the zonal and meridional currents combined at the epicenter of the earthquake. Again, we found that out from the NOAA paper. And we could, while editing it, I could see that there was a little bit of a bump around the tsunami time, which I found very interesting. So that concludes this video of the assignment 2. Thank you so much for watching.